Hello and welcome to this week's video. Again, this week we'll only be talking about Alibre because we have continued technical difficulties. I hope next week we'll be back to the Designing Any 3D Software series. But we're going to be answering a very interesting question that came up while discussing my other video, the one with the equation to create a fill area pattern if your CAD system doesn't have that tool. So a question came up of how you would fill an area with a honeycomb, right? So I'm going to answer this question in this video two ways. First, we'll create a honeycomb structure that adapts, that conforms to an area. In this case, it's a rectangular area, but the principle stands for other shapes, circular, rhombic, whatnot. So we'll have a honeycomb structure in here that will conform to these dimensions. And I want to have a frame that's 30 millimeters tall, and I want to have it 5 millimeters thick only on the outside. So this is our frame. Okay, so we want to fill this with a honeycomb structure that when this changes, the honeycomb structure will adapt and grow or become smaller along with the shape. And the second method is going to discuss about taking an area, taking a shape, and converting it to a honeycomb structure with very, very specific dimensions. Okay, so method one, let's start. I haven't created any variables yet because I want to show you what I'll be doing. So we'll make some assumptions first. We'll make the assumption that one side of the polygon is going to be on the vertical direction, and this point is then going to be on the horizontal edge. Okay, so one side is on the vertical edge, the other is on the horizontal edge, and the way this is going to work is I will create a honeycomb structure where I choose the number of instances along this direction, and then this entire internal area is going to be filled by a hexagon that follows that choice I made. Okay, so if you choose the number of instances along one direction, and because a honeycomb is made up by hexagonal structures that share their sides with the neighboring hexagons, that means that the number of rows of such hexagons is then going to be a calculated value. So if I choose the number in one direction, the other one is a fixed calculated value, okay? In order to fill an area, that is. The other assumption I'm going to make is that this is going to be a thin extrude. Let's make it 1 millimeter, okay? And it's going to be extruded towards the outside of my sketch. Okay, as you can see, the sketch is on the inside of my extrusion. So I will be making these two assumptions, and now let's go and make some variables. Okay, so we've got D1 is the length in the horizontal direction. D2 is the length in the vertical direction. Okay, D10 is the thickness I gave it. All right. So this is going to be, let's call it hex TH, and as a comment, I'll just say outside of sketch. Should be enough to remind me what's going on. Right. And actually, I say something here now. This is 30 millimeters. I don't want it to be 13 millimeters. I want it to be up to this surface. So when I change the thickness of the frame, this adapts, right? Let's go back into the equation editor. Okay, now, what else? So, as stated before, I'll be defining how many hexagons I'm going to have in the horizontal direction. So I make a count type of variable. I'm going to call it hcount, and I'll just say I want 20 hexagons. Okay. Now what that means is that there is going to be another value, which is going to be, I'm just going to call it hex flat, right? And that is going to be the dimension I'm going to use in the sketch for the opposing flats of the hexagon, or the diameter of the inscribed circle, right? Now you would think that this is a very easy, straightforward thing, like saying horizontal length divided by the count, and that's it. That's 20 divided by 200 divided by 20 gives 10, and it's not, right? It's not. So the actual equation is this: we take the length horizontally, and so I've opened the parenthesis up front, and we add that, I'm opening another parenthesis, 1 minus the count. I'll multiply that with the hex thickness of the 3D hex I just created, and then I'll also divide that again by the count of hexagons. So this is a correct equation, and as soon as I hit apply, it's wrong. Why is that? Well, Alibre says dimensionality not valid. It says that because I'm taking 1 millimeter and I'm subtracting from that distance of 1 millimeter something that is unitless, right? Namely the count. So the way you can circumvent issues like that is what I like to call the unit, the type unit. So I create a variable that is always equal to 1 and is of an appropriate type, so my equation works. In this case, I want to subtract unitless values, counts, right? So I created this variable, and I'm going to substitute this 1 millimeter. By the way, if I just erase the the equation works, and as soon as I hit OK or go somewhere else, it just puts it back there. So what I'll do is I'll delete this altogether, and then say 1 count minus whatever, and now this works, right? And that's the correct value. The equation before had an extra 0 here for some reason. So that is the correct value. That is the size of our hexagon. Okay, with that in mind, let's hit OK. We'll go back into this sketch. We'll say flat to flat, or the diameter of the inscribed circle is going to be this value. Hit OK. Check mark. That's it. Now, let's go into the XY plane and draw another hexagon. Okay. Now this hexagon is the one that shares this edge with our first one. So how are we going to position it correctly? So when we also thin extrude it with the thickness towards the outside, it falls on the correct location. Well, first of all, we want this side and this side to be equal. Okay. Then I will also project as a reference this side as well. I'll take a reference line. I want to grab the midpoint of this line, and I'll just leave it hanging in space arbitrarily. And then I'll use the midpoint trick in my Alibre tips and tricks series. So 1, 2, define the line segment. This is on the perpendicular bisector. Let's do it again for this side. 1, 2, define the line segment, and this is on the perpendicular bisector. Now, what that means is that this point is now the center of the hexagon, right? So that's one way to do it. The other way we could have done it, this entire thing, is to project the entire sketch to. That's another way to do it. Okay, but I still would have needed to create this line. So the way I like to do it is this. Okay, so I've made this line and this line equal. I'll make then the center here coincident to this line, right? And then I'm going to take the collinear constraint and say that this side and this outer one are collinear, right? So this is where this hexagon is going to fall, and I'll hit OK and extrude it. Let's look at it head on. Are we still on the outside? Yes, we're still on the outside, so this needs to be 0 and click OK. Cool. So we did these two hexagons, right? Cool. Now look at what will happen now. I'll take a linear pattern. I want to select both of these. I want to calculate the spacing that I want to use for this pattern. Okay. Now the thing is that if we are to share edges, let me show you what I mean. Right. If we are to share edges, I want a spacing so that this edge is repeated here. Okay, and if you look at this measurement, it says 10.05. So what that actually is, I'm going to call that h path distance. So what that is the hex plat, right? The sketch inscribed the diameter we calculated plus the thickness, but only once. All right, so xth. So this is the distance we want to use for our pattern. Okay. Okay. So this is the direction along which I want a pattern. This is the value for the distance. Well, it's going the wrong way. Let's change the direction. And now you will see that no. This edge. Now you will see that as I make instances, they do have these shared edges. These edges do not get any thicker because they are perfectly shared. Okay, how many of these hexagons I want to create? Well, of course, I know I want to create that many. Well, no, I don't want to create that many because I have a gap here. So I want to create that many plus 1. Okay. And you will see that there's no way around the fact that I'll need a final cut extrude to cut the pattern that is being created, right? So that it finishes within the frame. Okay, so we did the horizontal side of it, right? But I said earlier that the number on the other direction is going to be a calculated value. Okay. And how many of them are there going to be? Well, if we are to pattern these two rows, the height from this, right, let's take the measurement. Okay, so let's say that the height from this plane to this edge in the y direction is this number here, 17.4 something, whatever. Let's calculate that value now. Okay, and the way we do that is let's create the variable. First of all, let's calculate the spacing that it'll have. Okay, so without going into too much detail on how that works, the number is twice the horizontal pattern distance times the cosine of 30 degrees. Because Alibre needs radian in here, that is how we convert it. So this is the number of degrees, and we convert it by multiplying by 2, multiplying by pi, and dividing by 360. So that is the vertical pattern distance. Okay, and now that we have that value, we want to calculate how many of them we will have. So again, we can tolerate pieces of a hexagon sticking out of the frame because we'll cut around it, but we can't tolerate not filling all of it, right? So we want to be rounding up, okay? We want to be creating a count type. Okay, so this is v count, and let's rewrite that. So then v divided by v pattern distance. Okay, so that is the number 6. Okay, now you can clearly see, because this is less than 20, and 20 times 6 is 120, this times 6 is going to be less than 120. So this is just the integer part of this division, okay? We are dividing two distances that are in millimeters, so the millimeters cancel out and it becomes unitless, so it can go into the count type, right? But what comes into the count type is only the integer part. So this is 6.9 or whatever, and we need to add 1 to it, okay? Because this is how we round up. We take the integer part only, and we add 1. Okay, so this is good. Now we're going to go back into the same pattern, and we're going to say that this is the second direction. This is the pattern distance, and how many of them do we need? Let's open v count. We need that many of them. Okay, and it's going to take a while to calculate, and it has calculated. So here we are. Okay, and we hit OK. Okay, and now all we need to do is to cut around and clean this up. So we're going to go back into the XY plane, and I'm going to create a center rectangle. This is vertical. Okay. So this is a length horizontally plus the thickness from extrusion 1, which is d6. All right. Okay. No. No. This is the length horizontally plus d6. Well, it's plus twice the d6, obviously. And then this is the same thing, length vertically plus twice d6. Okay. And then we're going to create a second center rectangle. Again, we need to stop it from rotating, so let's make this horizontal. And I'm just going to do it quick and dirty. I just need to make sure that this outer rectangle is far away enough to cut all of these extras all over the place, right? So I'm just going to put a line here, say that this line is coincident to the center, okay? Then I'm just gonna give this one, I'm just gonna create this distance. I'm going to say that this is twice the hex flat value, which was, if you remember, the size of the hexagon we created. Okay, deactivate that. We extrude cut through all. Okay, and we're done. That's it. We have our hexagon pattern. Okay, now let's see if it is indeed parametric, right? Let's bring it over here. Let's say this, let's change D1 and D2. So length V and length H. Okay, so let's change this to be 150. Change this to be 70. Okay, numbers should be changing all around, and let's hit OK. So here it is, right? Now, if you count these hexagons down here, they are 20. Okay, and 7.55. So it did what it was supposed to do. It shrunk the hexagons so that they fit in the new frame. Okay, let's change the number of hexagons to, I don't know, 17. Let's hit OK. Let it calculate. And there you go. Okay, fewer hexagons, so they are made bigger. So now this is a completely parametric honeycomb structure within this frame. So for the second method, I'm just going to create the honeycomb structure floating in space. Right? I'll start at the origin. And I'll make this side horizontal, and I want to make the inscribed diameter, the diameter of the inscribed circle, 20. That means that also the distance between flats is 20. Okay. And then I'm going to create two reference lines, one from the center of the polygon and the inscribed circle to the middle of one side, and then one from the center again to the middle of the next side. And I will use these two lines to create axes from sketch. Okay, so I select this, hit apply, I select this, hit apply. So my sketch is done. Okay, I will thin extrude this now. I'll extrude this for 30 millimeters. I want a thickness of 1 millimeter towards the outside. So this is the outside, this is the inside, so 0. And this is my hexagon. Okay, now I will pattern this because I don't have anything else to pattern. And my first direction, my first linear path is going to be the first axis I made. And the spacing is going to be this. As we said earlier in the video, the diameter of the inscribed circle, so D1, plus 1 times the thickness. Okay, so D5. Okay, now there you go. This matches perfectly. The way you know that it matches perfectly is because the thickness of this edge is the same as every other one. Okay, if it was off by, let's say, 0.5 millimeters, you would see that this edge is thicker than it should be. So that's how you know you're doing everything correct. Okay, and let's say now that the other linear path is our second axis. And our spacing is indeed again D1 plus D5. There you go. And you can see that we're starting to create a honeycomb here. I'll just turn the preview off because the honeycomb structures can become very heavy very quickly. Okay, so I want 20 by 20 here. It's a large one. And I will turn the preview off. I'll hit OK, and I'll bring you back as soon as this finishes calculating. Okay, so we're done. We have calculated. Okay, now we have a honeycomb structure. And actually, I really like honeycomb structures. I don't know why, but there you go. So we have a honeycomb structure here. Okay, and I will save this. And I will name it I will name it honeycomb structure. Very imaginatively, I will name it honeycomb structure. Okay. So we saved this, and I will exit out. I will make a new part. So I made the hexagon 20 millimeters, and I'll sketch again in the XY plane. I'll make the hexagon 20 millimeters, and I have 20 of them on either direction. So, you know, I'm sure to cover an area that's, let's say, 300 by 300. For sure, I'll cover an area this big. So I create this rectangle as a guide, right? You will see why, and of course, if you need a larger honeycomb structure, you just go back and add instances, right? Or make the hexagons larger, or whatever you need to do. So let's take a spline and create an abstract structure. Okay, so this is it. I'm not going to dimension it. I just want to show you that you can create whatever structure you want here, right? So let's give it depth of 8. Okay. And now I will turn this into a honeycomb structure, right? How am I going to do this? I will use Boolean intersect, and I will use the honeycomb structure I just made to turn this face into a honeycomb. It'll take some time to insert it, so let's wait. There you go. So I'll put it in. I just want to constrain it now so that they're on the same level. They start from, the same plane. Okay. And then, okay, we can close that. And then I'll just move the honeycomb structure by hand so it covers all of it. Of course, if you need to be more precise, you can definitely be more precise than this. Okay. So now, if I hit the check mark, look what's going to happen, right? By the way, I really love Boolean intersect. Yes. So we turn this thing into a honeycomb structure. And what's more, we can do this. Let's create another sketch on the XY plane. I'll project to sketch, my original sketch. I want to create a sketch figure. I want to maintain association, but I don't want to project any reference figures. And there we go. Okay, so now I'll select this. I will thin extrude. I want 1 millimeter. No, I want a 2.5 millimeter thickness, only towards the outside. Okay, so this is going to be 0. Right? And I want to extrude up to this geometry. Right? And I have now created an oddly shaped grill, right? Filled with hexagons. So this is just to show you that you can create any shape you want and fill it with hexagons using this second method. And also you can create this honeycomb structure and add it to the library, as I show in my 3D form thread video. And then you can change the size of the hexagons, how many there are, whatever, so that you can adapt this to any shape or form you want to turn into a honeycomb structure. Okay, so I'll just save this so I can add it to the forum thread, and you guys can download it from there. So that's it. If you liked it, hit like. If you didn't, hit dislike. I still want to know if you didn't like it. Subscribe and check the notification bell for more videos like this. And I hope I see you in the next one.